our objectives, as I've just tossed things on the floor, solve polynomial equations. We've done that in the past, so we're just going to review it. Solve rational equations, same thing. Absolute value, which ironically algebra 2 class is doing right now. Radical equations and equations with rational exponents. And then the last one, solving equations in quadratic form. Okay, so this is a good review. It's just going to be a mashup of a lot of examples put together. Okay, and it's going to be like an example of like almost each type of this, to where you at least have a good reference as you're going through it. I have 2 quick warm-ups. We're just going to answer these together. If I had this equation, how many solutions would that equation have?
7.
Okay, 7. We all agree with 7?
Yeah.
Yeah? I would agree too. So yeah, 7 solutions. Okay, and how do we know it's 7 solutions?
Because what's it called? There's like a word for it. It's the highest power of the polynomial.
Yeah, degree.
It's 7, therefore there must be 7.
Very good. Yeah, it's the largest degree that tells you how many answers. Now, problem 2 says this. What theorem helps us to decide the number of solutions for like equation 1 has? Do you remember what the theorem was? That's a long time ago. So the theorem is fundamental theorem of algebra. I know, not very snazzy with the name. But that was developed, the first proof of it was developed by Carl Friedrich Gauss, which we talked about Gauss last year. We talked about how he was able to add the first 100 digits in his head really quick. So very, very important person that we'll be seeing a lot of. Okay. Here we go. So we're going to start with the first objective. First example. So we're going to be solving a polynomial equation. Okay. When you have something with 4 terms, 5, 6, okay, as it keeps going on, a good method to maybe try to solve is just group it. Group things together and see if they have something in common, okay? I'm gonna try grouping the first 2. And by the way, you might have to rearrange this to see if your grouping comes up with something like a GCF. It might not at first. But typically, if it's written in descending order, you could just group the first 2 and the last 2 of the equation. So now, given this, let's see if we can't factor a GCF from each term, okay? And the goal is when we factor that GCF, we want the exact same thing in the parentheses. So here I can take out a maximum of x to the 4th, so I'm left with x squared plus a 1. On the other side, again, I want this to match over here. These are both positive, so I should take a negative out here as well. So we'll do a negative 9, and we get an x squared plus 1. Okay, which is perfect. Wow, I cannot hold things in my hand. Save my life. There we go. So when we factor by grouping, we want this to happen. Okay, if it doesn't happen, then maybe you took the wrong GCF out, which is possible. Now I'm going to factor this out of the whole term. So I'm going to take this away from both of these. Okay, so x squared plus 1, I'll take that away. What's left is the x to the 4th, and over here is the negative 9. Okay. So if you notice, what we had originally, not very, I don't want to say user-friendly in terms of solving it. Now we have something that seems solvable. We have 2 things equal to 0, so we can use the zero product property. So for the first one, we'll set x squared plus 1 equal to 0. Subtract the 1, and then take the square root. So that's plus or minus I. So it had 2 imaginary solutions. Now this over here, it's very tempting just to put, 9 over and then take the 4th root, right? But there's more kind of lurking inside of here. okay? Remember with even power roots, you could have what, a positive or negative component? Remember that? Like square root's a positive or negative component. So what we're gonna do here instead, see how x to the fourth and 9, they're pretty much perfect squares. What times what gives me x to the fourth? X squared, right? What times what gives me 9? 3 times 3. And there's no middle term. So when I factor this out, I can do x squared minus 3, x squared plus 3, okay? So at any time when you're trying to solve some of this, and you have a perfect square here and here with no middle term, you could factor it. All you have to do is the factors that give you the perfect square are on the outsides, and then the signs are different. So now what I can do is set each one equal to 0. Okay? So then this will just be x squared equals 3. Bless you. So x is equal to positive or negative square roots of 3. And then on the other side, we'll subtract 3. And then take the square root. And that's the square root of negative 3, which I'll take the I out. Now that we know how to use that, we get plus or minus I squared of 3. So my solution set, I got some space here. We get positive negative I, positive negative square root of 3, positive negative I squared of 3. Now, does that match our polynomial? Well, look at the warm-up we just did. We were supposed to have 6 answers, 2, 4, 6. We're good. See, Gauss was pretty smart. All right, let's try another one. Same instructions, we're just gonna solve it. Now, even with quadratics, we still want to set this equal to 0. It makes it a lot easier for us to figure out what technique or what procedure we want to use. So let's go ahead and do that first. So x to the 5th minus x squared equals 0. Okay? Now, just like the first example, I took a GCF out. Guess what I'm going to do here? Take a GCF out. So what can I take out of both of these then? An x squared, very good. So x squared comes out. I'm left with x to the 3rd minus 1 equals 0. And if you're ever unsure, I mean, could you just multiply this back in and see if it gives you the original? Yeah, absolutely. Zero product property, set each equal to 0. Well, I think we get 0, huh? So x is just going to be 0 there. Take the square root to both sides, that's not really going to change anything. Okay? But I will say that even though if I put a positive or negative here, I'll just put it here right now, this is still counts as 2 solutions. They're just both 0. Okay? So it's considered as 2 solutions. And we'll talk about more with that later in the future, because graphing this, which we'll start graphing some of these polynomials, having something that's the same, whether it's positive or negative like that, like a 0, indicates like a balance, and you'll see that a little bit later. Now on this side, just like that guy over there, it's very tempting to what? Add 1, take the cubic root, and you're done.
Pardon the interruption.
No.
We need all Career Center students
Okay.
to please go to the auditorium. All Career Center students, please go to the auditorium. Thank you.
Okay. But anyway, I don't want to add the 1 over. Remember how we broke these apart? This is a cubic. That's a cube and 1's a cube. Okay, so we could break it apart. Because there's more than just one answer there. There's 3 answers. This is how we're going to do it. We're going to factor this cubic out. So what do you cube to get x cubed? X. What do you cube to get 1? 1. Now the sign that goes there, I taught you last year, it was so kind of corny, but it works. So we're going to take the same sign here, the opposite sign here, and then AP was always positive, right? So now, what goes in this position? Well, it's this guy squared, so it's x squared. What goes in this position? Multiply these two together, and you just get a 1x. I'm just going to put an x there. And then the last position is this square, so it's just 1. Okay, so again, we've done cubics in the past, it's just been a while. So now we're going to set each one of those equal to 0. And solve. Now, just to take a back step, if I would have added 1 to here and took the cubic root, that was 1 answer, right? So I got 1 answer, 2 answers, that's 3. I should have 5, right? So always go back to the original. Did I find all the answers? If I didn't, maybe there was something I missed. So this will just give you a 1. Over here, that sucks. It can't be factored. So, I mean, we could do complete the square, but we get some fractions. So, bless you. I just did a quadratic formula. So when all else fails, we know that that would work. So let's go ahead and use quadratic formula. So again, x equals -1 plus or minus 1 squared times 4 times a times c all over 2 times your a. Okay? All right. Now, this becomes x is equal to -1 plus or minus. Okay, solve what's underneath there, you get -3 over 2. Almost done. I know, it seems like a lengthy problem for something that didn't look like that at the beginning. I can take an I out to finish. There we go. Okay. So that's 2 answers. That's 3, that's 4, that's 5. So I got my 5 answers. I'm good to go. I found them all. So my solution set, we'll put it all together, would be, well, like I said, plus or minus 0, but it's still 0. 1, and then -1 plus or minus I squared root of 3 over 2. Okay, so those are all my answers. And just like I said in a prior lesson, see how my answers are kind of scrambled? So it's nice to be able to rewrite it afterwards so you can see exactly what you were figuring out. Okay. Cool. Let's try, so these are polynomials, so we're gonna do the next objective. Let's go to rational equations. Solving rational equations. Okay. There we go. This looks kind of familiar, right? We've done something like this before. We've hinted at some of this stuff already, so it's just kind of putting it all together. I want to get rid of the fractions again, right? It makes it a lot easier when the fractions are gone. So that means I got to multiply by an LCD. But to find it, I need to break this down a little bit further. Okay, so let's do that. So could it be factored? The answer is yes. Factors of 4 that give me -5 when I add them, well, that's going to be -4 and -1. Typically, not all the time, but I told you as like a little bit of a hint. Sometimes the other 2 factors here are going to pop up here, or maybe just one of them might, okay? Not all the time, but a good majority you sometimes see that. All right, now the LCD part. Well, my least common denominator would be both these factors, right? If I multiply everything by both these factors, I would get rid of the fractions. So I'm going to multiply everything by this, okay? So everything's going to get x minus 4 and x minus 1 multiplied to them. Okay, so if I multiply this to the first fraction, they're going to cancel out. I'm just left with 3. Okay, shouldn't say cancel, they reduce. That's honestly the proper term to say. It reduces down to 3. Okay, over here, we know that the x minus 4s are going to reduce, so it's just going to be an x minus 1 left. And multiply by 1, hey, we still get x minus 1. Lastly, the x minus 1s are going to cancel out. I'm left with just the x minus 4. That's going to get multiplied to this guy. So x plus 5 and x minus 4. Okay. That looks a lot easier to work with, right? Because originally, this could get kind of messy. So it's good to be able to come down to something a little bit more generic, a little bit more, well, quadratic, as we're gonna see soon. Now, before we continue this, I wanna make a note. Bless you. If you look at the equation that we started with, what x values should I not get? Or I don't wanna have, I should say. What would it be?
4 and 1.
Okay, we all agree, 4 and 1? So if I get a 4 or 1 here, guess what? Can't be an answer, right? Okay, so let's just do that. So x cannot be 4, x cannot be 1. All right? So let's solve. Multiply these together. Now, hopefully by now you can start doing a little bit of mental math with this. So we know we're gonna have an x squared. Now, if I multiply the outside, it's a negative 4x and a 5x. So that's just a plus x. And then multiply the last, you get 20. So again, I'm trying to skip that step where you combine the middle term. I'm just gonna jump to the middle term. Let's set this equal to 0 and combine terms at the same time. Okay, so this will be a 0 now. X squared, because there's no other x squareds. An x and an x is a 2x. So we get 1 minus 20, so that'd be a negative 19. But we're also subtracting 3, right?
Would it be negative
Oh,
1?
negative 1. Thank you. Where did I get plus 1? I don't know. Brain just decided to switch it. Sorry about that. So yeah, negative 1 minus 20 would be negative 21. Take 3 away, we be negative 24. There we go. Okay. We have our methods. Again, just like this guy, I'm going to try and factor because that's a little easier, a little bit cleaner. So factors of negative 24 and then add to give me 2. Well, I think that's 6 and negative 4. I think that works. So here we go. So x minus 6, sorry, plus 6. I did it again. And x minus 4. It's my hand. My hand doesn't want to work today. Doesn't want to write the right things. So if I set both equal to 0, I'm going to skip that step. I'm just going to jump to the answer. So we get negative 6 and 4. We set both equal to 0. Okay, well, which one's good? Negative 6, right? This guy, nope, can't do it. Because we already established that it's not going to work. So therefore, only that is my solution set, so negative 6. Okay? Now, you should always, and just to save time, you can always, plug it back in to make sure it does work. And this negative 6 does work. All right. Moving on. Let's try a word problem now. Guess what? Mr. McCullough, I'm always doing something. Takes his kayak. I went boating, now I'm going kayaking. 8 miles downstream. With a 2.5 miles per hour current. Okay? Current's with me. I'm speeding. All right. The return trip. Wow, that's not how you spell return. Try that again. Ooh. There you go. Return trip. Against the current. Yeah, if I spell something incorrect, you're going to see Hendrix walk in here and just bust me down. Takes 1 hour longer. Okay? So yeah, I go downstream, I'm having fun, and then they say, by the way, you gotta go back upstream. Okay. Takes me a little longer, which makes sense. You're going against the current. So what they want to know is, find the speed of the boat, which it's a kayak, so kayak, in still water. Okay? So take the current out of it. What's my speed? without the current hitting me, okay? So I don't know what that is, what my speed is in current water, or still water. So I'm gonna let B be that. So B would just be the speed of the boat. I keep saying boat, it's kayak. But speed of the kayak in still water, okay? So without the current. Now one of the things you learned many moons ago was if you want to find the distance to anything, it's your rate multiplied by your time, right? Okay, so your rate would be like miles per hour, meters per second, feet per second. Time is always measured in seconds. And multiplying those together gives you the distance, all right? Well, looking at what I have here, okay, I know it's going to be at least 8 miles downstream, which is good. We're going to need that. But that's not going to help me find the speed yet, okay? Instead, what I'm going to do is I'm going to work with the times to find the speed. So if I rearrange this, like divide both sides by r, I can find the time spent of me kayaking by taking the total distance and dividing it by my rate, okay? That's the approach I'm going to take for these problems right here. So let's make a small little table. So with the current, okay? So my distance is still 8 miles. That doesn't change. My rate, well, it's the speed that I'm going plus 2.5 miles per hour of the current with me. And then we already said what the time is. The time is just going to be my distance divided by b plus 2.5. Okay? So those are my stats with the current. Against the current, okay? The distance is still 8 miles. But my rate changes, right? If I'm against the current, well, that 2.5 that I was experiencing is now against me, right? So it's my speed minus the current speed, which is 2.5. Okay, so that's a little bit different. But my time, I'm still going to divide the two. So it'd be 8 divided by b minus 2.5. Okay? Now here's the deal. It took me what, 1 hour longer to go back up, right? So if I take my time with the current and subtract, take my time against the current, sorry, I flip-flopped it. If I take the time against the current and subtract with the current, it should equal out to 1 hour, because that's the extra time, okay? So that's my equation I'm gonna set up. So I'm gonna take the against time minus with the current time. And it should come out to be 1. Okay? Because again, 1 is that extra hour. And I was tired afterwards. So let's put in the times. So against the current was 8 over b minus 2.5. We're going to subtract with, so 8 over b plus 2.5, and then that's going to equal 1. All right? But this is key. I mean, can you skip to this step? Yeah, but it's good to have some of your stats written out first, so that way you know how to even approach this. All right, multiply by an LCD. So I'm going to multiply everything by b minus 2.5 and p plus 2.5. Okay, so everything's going to get multiplied by that. So for the first part, these are going to reduce out. So it's just b plus 2.5 times 8 is here. Next one, the b plus 2.5's cancel. This is the only one left, so b minus 8 times b minus 2.5. Okay. And then the other side, well, they don't reduce at all, right? So you're just going to see both of them over there. There we go. Okay. Looks a little messy, but we're going to clean it up pretty quickly. All right, let's distribute. So we get 8b plus 20 minus 8b plus 20. Okay. Hey, you saw it twice, huh? Just a little sign difference with the variable. On the right-hand side, I'm going to be smart about this. It's the same binomial, just the signs change. Therefore, no middle term. I'm going to multiply the outsides only then. So this is just going to be b squared minus 6.25. Okay? So again, just playing it smart. You know, you already know what that pattern is, so use it. These guys are gone. I'm left with 40. B squared minus 6.25. So we're going to add that to the other side. And then, of course, my last step is to take the square root. Now, I want to be very clear on something here. When we take the square root, we have a positive and negative, right? But the negative isn't going to match with this problem, because we're talking about time. So we're only going to consider the positive case. So in this case, actually, I'm sorry, speed, not time. I misspoke there. So it's going to be 6.8 miles per hour. Okay? Told you my arms were killing me. Going that fast in a kayak. I honestly don't know if I could. But it is fun going in a kayak. Okay? All right. So, I think we're on to absolute values. So let's try some absolute value stuff. Recall from your Algebra 2 days. So the absolute value of a value is its distance from 0 without regard to its direction. That's what we talked about in the past when it came to absolute value. So a good example of that is something like this. Okay? So what that reads is the distance x is from 0 without regard to direction. It doesn't matter if I go on the left side of the number line or the right-hand side. The distance has to be 5. So what are those two cases? Well, easy. X either has to be 5 or x has to be negative 5, right? Those are the only two answers. These are the only two numbers who has a distance that's 5 units from 0. Okay? Now, an algebraic definition. A little bit more formal here. Something you'll see a lot of. Okay? We can define the absolute value of, in this case, u. Use any number. Okay? It becomes positive if, okay, u is greater than or equal to 0. So that's one of the outcomes, right? You could have a positive u value here, or you could have a negative u value in here. Still gives you the same answer, but that occurs when u is less than 0. Okay? So those are our two cases to consider there. Is there a really? Hello? Hey. I do. Anyway, but yeah, we have to consider a negative or positive in here. Okay, and that's all this definition is saying. It's just to consider those two cases there. So let's just write that underneath just to generalize it. So, absolute value of u is some number k means that either u is equal to k or negative u is equal to k. Okay? So, some properties with this. This underneath. So we're going to let k be a positive real number. Okay. So our first property, which we already kind of wrote up there, absolute value u equals k is equivalent to u equals k or u equals negative k. Second property, I'll move out of the way here. Absolute value of u is equivalent, okay, to u equals 0. That one seems obvious. You don't have two cases for that. It has to be 0. Man, these markers don't want to erase. I think I might prefer chalk ones. I don't know why, I like the sounds they make. So 3, absolute value of u equals negative k is equivalent to no solution. Let me give you a small example over the side there. So that's something like this. If I had the absolute value of x equals negative 4, well, there's no number that's a negative 4 distance from 0. Okay, distance is always measured positively, so that would be a no solution type problem. Okay? Next, fourth property. Absolute value u equals the absolute value w is equivalent to u equaling to w or u equaling to negative w. So even though we have two absolute values stuck together like that, we're still treating it like we did over here. Either this has to be a negative version of it or a positive version of it, okay? And technically you can go the reverse direction. Okay, you could say that w is equal to u or negative u as well, okay? So direction doesn't matter in that case. Now your textbook stops there. There's two other properties I want you to know, because they do pop up. I just don't know why they don't mention it, okay? The first one's the multiplication property. If you're multiplying two numbers, you could separate them into the individual absolute values, okay? So this is an important one that we'll see here. And then the last one, I use this a lot in college, especially grad school I did, so I want to make sure you guys at least have seen it. It's called the triangle inequality. Okay? So you could take the addition of two values inside absolute value, and that's less than or equal to the individual absolute values added. Okay? That looks like a weird W. Let me change that. So again, this is another one that we use a lot in mathematics that pops up periodically, especially in different proofs. So I just want to make sure that you at least have these in your notebook. And again, if you ever see it in the future, you have that with you. Okay? All right. So let's start solving. Okay. Let's do this example. Okay. Now, notice though, the absolute value is not by itself, right? So it's hard for me to jump into what it's equal to if it's not by itself. So let's subtract 2. So the absolute value of 2n plus 4 equals 10. Now, this matches what we said over there. So let me make this a little bit more clear, because sometimes the definition might not be as clear. So this is what it's telling me. Either this has to be a 10, right? Because the absolute value of 10 is 10. Does that make sense? Or this is what? Negative 10, because the absolute value of negative 10 is 10. So those are my two situations, right? So let's write that down. So either what's inside is equal to 10 for that to work, or what's inside is equal to negative 10, which absolute value gives you 10, okay? And just to connect it back to the definition, that's the part that's without regard to its direction. All right. So solving this, I'll subtract 4, and then divide. Okay, we get 3 for that side. Repeat the process, I'll subtract 4, and divide, I get negative 7. Now, to save time again, because I don't want to, because we still have more examples to go, both solutions work. You should always check, okay? So always check solutions, but in this case, they do work when you plug them back in. Okay? All right, let's try this example. All right. So absolute value of x minus 2 equals negative 5. Well, if I look at this, I'm done. right? What's this telling me?
No solution.
No solution, right? So just empty brackets. Yeah, this saying the distance this is from 0 is -5. We know that that doesn't quite work out for us, so yeah, that's a goner. It's done. Yeah, I don't know what they did to these boards over the summer, but not good. Okay, part C. All right, let's try one of these ones. So we did one example where we did get solutions, one that we didn't. Okay. Now we're gonna try one that has two absolute values. So again, let's just go back to the definition of it. So either this is equal to the positive version of this, right? Or this is equal to the negative version of this. So I have 5x minus 1 is equal to the positive version of it, or 5x minus 1 equals the negative version of it. Okay, so I'm going to put a negative sign on the outside of it. By the way, it's okay if you flip it. You could actually do this as the positive and the negative version of it. You could read it from the other direction. So it's like you're reading it backwards, but this is the forward way of what everyone uses. Okay, combined terms, I'll take the x over. Maybe, if I can write it. Okay. We'll add the 1. Get -1. Okay, and then we get x to be -1/4. On the other side, I'll distribute the negative first. Okay, and that's important too. The negative has to go to every part, not just the x. So I'll add the x over, make it 6x. Okay, we'll add 1. And then we'll divide, which I'm also going to reduce at the same time. We get a half. Now again, I am going to save us a little bit of time, but if you plug both of these back into it, they do come out good. So my solution set is -1/4 and a half. Okay? All right, last absolute value one I want you to look at. And I'm trying to do one of each case. That way you have a good example with it. So the last case I want to explore is this guy. Right? And this is where I differ a little bit from the textbook. And the reason why I differ from it is because I'm using
Pardon the interruption.
Really?
Can the following
This
students
property.
please report to the auditorium at this time? Emma Anderson, Mila Barber, Isabella Boblitz, Jaden Beaver, Jacob Berry, Lorena Bright Stanaway, Mackenzie Cowdery, Peyton Gray, Aiden Hassan, Gabby Heaton, Olivia Jackson, Carter Lemus, Addison Lucas, Austin Pickering, Jackson Raybach, and Zayden Ross. Please report to the auditorium at this time. Thank you.
They probably didn't take into account they're probably in the cafeteria, but you know, that'll hit them later. Okay, these almost look the same, right? They're very close to being identical. The only difference is this one's what, the negative version of this guy, right? So what I can do, using that property over there, I can take a -1 out, because again, this is the same thing as this. And what's the absolute value of -1? 1. So this is just 1 times this, so guess what? They're the same. They're identical. Didn't look like it at first, but using some absolute value properties, they are the same. So therefore, the solution set is all real numbers. Okay, I can put anything I want in there. So if you come up to this opportunity using that property of multiplication, you can take a -1 out, and then that becomes 1, so you get the exact same equation there. Which, hey, I think that's pretty cool. All right. So we're on to radical stuff. Let's talk about radical equations. Okay. So quick recall. So an equation with one or more radicals, remember that means square roots, okay, containing a variable is called a radical equation. Okay? So as long as you have a square root in there, we're calling it a radical equation. Okay? Now, here's something that's important, something to highlight here. Okay? So not all solutions, can't write, to a radical equation are true. Okay? That's important. We could come up with answers, even though we did everything correctly. That's the key part. You did nothing wrong. And you'll see why this is the case, but your answers at the end might not all work. Okay? So I'm gonna just cut this short. So we call these solutions, I'm gonna abbreviate that, extraneous, which you've heard of that in the past, solutions. Okay? So if any of those do not work, we call this extraneous solutions. Okay? All right. So, let me go ahead and try an example out. Okay. Let's try this one. So, just solve. I can write this down. There we go. So there could be a possibility that when we solve this, we'll get an answer that doesn't work. Okay? And honestly, here's the cool part. The visual, if you remember what square roots are as a visual, it's something like this, right? So if I have two of those on a graph, they could be crossing at one point, right? So that's something to just like think about. Maybe one's going in this direction and, I don't know, one's coming like beneath it. So they intersect at one point. So that's like a possible answer that we could get. So how do we solve this? Well, to get rid of the square root, we gotta square it. So we're gonna square this side and this side. Now the left-hand side is the easiest. You just get what's underneath the radical. Perfect. Okay, the other side, well, not bad, nothing terrible. I'm gonna put it over here as a reference as we're multiplying through it. Okay. There we go. So let's see, 2 times 2, that's 4. Now, the middle term. It's gonna be 2 times this guy. Now, I can't multiply 2 to both of these because of square roots, so it's just gonna be 2 square roots of this guy. And then I multiply these together, guess what? I get another 2 square roots of this guy. So that's a total of 4 of those. So plus 4 square roots of 8 minus x. And then multiplying these last ones together, because they both have a square root, that's a half power, right? So a half and a half gives you 1. It cancels that out. So you're left with plus 8 minus x, what's under the radical. Okay? So a lot going on in that one, huh? Quite a bit going on there. Okay, let's try and simplify as much as possible. So we get 5x minus 4 equals, the 4 and the 8 gives me 12, minus x, and then plus 4 square roots of 8 minus x. Okay? I know, that square root's still there. That's a problem. we gotta do something about that. But first, let's get everything to the other side. So I'll add x over here, and I'll subtract 4. So I'm gonna do that all in one go. So that'd be 6x, okay? That'd be minus 16 equals 4 square roots of 8 minus x. Okay? So, still got a square root. That sucks. But I can get rid of it. I'm gonna square everything again. So let's square both sides. I know, might seem like that's gonna get ugly, but we'll get through it. need some more floor space. Okay. So, this square, again, I'm going to square this guy, multiply them together, and double it. Okay, so I'm going to do that all at once, just to save a little bit of time. So this would be 192x 256. Okay. On the right-hand side, I'm going to square this guy here. So I get 16, and then what's under the radical, 8 minus x, because remember, that cancels this guy out. So the right-hand side came out nicely. Now, before I go any further, I want to talk to you about this. We started with a square root function, right? We ended with a quadratic. Quadratic has two answers, right? So we transform this into something completely different. So even though the answers we find will work for this, it's not a guarantee it's going to work for this, because we actually have two different functions here. So we transformed it into something else. That's why these could happen, okay? All right, so I'm going to multiply this to both terms. So we get 36x squared minus 192x plus 256 equals 128. That's a weird 128. Minus 16x. Okay? So combine them all together. I'm going to do this all in one move. Again, just to save you a little bit of space in your notebook, and we know how to combine terms. So this is going to end up becoming, when I simplify, 36x squared minus 176x plus 128 equals 0. I think when people see high numbers, they're like, I did something wrong. You didn't. It happens. It really does. So now what do we do? Well, I gotta solve that. I don't want to. That seems kind of, doesn't seem like the nicest thing to do. There's no factors that will work. And complete the square, I have to divide everything by 36. So let's use quadratic formula. So I think that's what we're gonna do. So let's see, b is negative 176, c is 128. Okay? I mean, the quadratic form is nice to handle those large numbers anyway, so it's no big deal. All right, so this becomes a positive 176 now. Okay, so there's just me plugging those values in. Okay, and again, just to save a little bit of time, I'm going to tell you what's underneath the square when we're done. So it's 12,544. I know, that just rolls right off the top. Again, large numbers is like, oh man, really? But it happens, it really does. So we have two options. We can add the 176 to this, divide by 72, or subtract it. So when we do that, these are the two answers we get. We get roughly, I think it's, actually it comes out nicely. I would get x to be 4 or x to be 0.89. Okay, so those are my two answers for that. Now again, I have to check the solutions, because again, one of these could be extraneous. So I gotta plug these back into the original. So I'm gonna put that note here. So plug back into the original equation, okay? Now, when we do that, only one of these will work, okay? And you can probably guess it's gonna be the nicer value. 4 works, this guy doesn't, okay? So this is gonna be our extraneous solution. 4 is good, so my final answer is just 4 for that guy, okay? But again, the main reason as to why that is the case is because we're transforming it into a quadratic. And that's where things get different. Okay. Now, here's what I'm going to do, because we're getting close on time. I'm going to give you one more example, okay? Tomorrow, I'll give you one more to finish it. I just don't think I'm going to be able to do everything here, okay? So, let's talk about quadratic form. Okay. So what we can do is we can create a quadratic when there's no quadratic that exists. Okay, so let's go ahead, let me give you an example. This kind of, it has some similarities with that project you guys are working on too. Okay, so let's say we get something like that. That's brutal. Can you imagine squaring both of those, multiplying by 26, and then using, well, it would be a quartic, and try to figuring that out? That's a little bit, too much. So what can we do? Well, notice that we see this coming up twice, right? See how they're both the same? So what I can do is called a use substitution method. I can make that more generic. So if I let u be 3x squared minus 2, I can go ahead and rewrite this as u squared plus 26u plus 48 equals 0. Okay? Now, I don't know about you guys, that looks a lot more simpler to solve than the original, right? But when I'm getting answers, I have to plug it back into my substitution to know what the x value is. Because right here, I'm just solving for u values. But once I have it, I can plug it in here to find the x values. A lot simpler of a process than dealing with the original. Now this I'm going to solve by factoring. Okay, that would be a lot easier to work with. So it'd be factors of 48 to give me 26. That's 24 and 2. Okay. So solving it, this will be negative 24 and this will be negative 2 when I put them both equal to 0. Okay. But don't stop there, because again, what you found was the solutions to this quadratic. Okay. So what I have to do is use these guys into my u substitution to figure out what the x values are that make this true. Okay. So now sub back in for u to find x. Okay? And by the way, we use u substitution a lot in mathematics. So if you're going to take calculus, you'll do it with integrals, with sometimes derivatives. I mean, there's a lot of applications for it. So up here, let's take u out and put negative 24 in its place. And then the other solution would be negative 2 equals this guy. Okay? Solving it, well, we'll add to the other side. Okay. Divide by 3. Well, that doesn't look good already, huh? And that's fine, but think about it. We found this answer a lot quicker, even though it's not the nicest, than rather than dealing with a quartic and trying to figure that out. So I'll take the square root, I'll put it up here. So it's plus or minus the square root of negative 22 over 3 equals x. Okay, and what I'm going to do is take the I out to finish that one. 22. Okay, so there's two solutions. So two of these solutions were imaginary. Okay, the other side. So I'm going to add 2, I get 0. Okay, and well, we can probably stop there because it's going to be 0, right, as my answer. When I divide by 3, I get 0, and then square root. But this still counts as 2, because remember that's that plus or minus situation we talked about at the very beginning. So this still counts as 2 solutions. They're just both 0. Okay, so my solution set is going to be plus or minus I square root of 22 over 3, and then 0 for that guy. Okay, and again, I'm still getting 4 solutions, because this would be what, to the 4th power? So that's 2 here, and that counts as 2 as well. So I got all the answers I need. Okay? I'll show you one more quadratic form problem tomorrow. It's with exponents of fractions. Okay, so we'll do that tomorrow, and then we'll do some practice with it, okay? Sound good?